All right, I think it's a good time to kick off. So, hey, good morning, everybody, and welcome to the Cloud Practitioner webinar series. My name is Ursula. I think most of you know me already, so not going to do like a proto introduction today. Today is going to be about databases on cloud. So we are going to talk about what's the differentiator when we build databases in a cloud environment, in a global cloud environment. But much more importantly, we are going to talk about what are the database types that we have. So we are going to cover the areas that you will need to know and manage in order to pass the certification exam. But there will be also content that is outside the topic area. So the actual topic area for the certification exam is quite narrow. And I'm going to mention that when I'm talking about topics that will not be seen in the exam phase. I have a lot of content, and I may actually do it so that I will first cover basically the mandatory topics that you need to understand in order to get through the exam. I will take a couple of topics outside that, but I may actually take a practical example at the end. And remember, next week we have an immersion day, so that's next Thursday, and there you will get to experiment with database products, different kinds of database products that we will talk about today. So, hey, let's get going. And let's talk about databases and what is perceived as database products when it's the cloud environment that we're talking about. So we'll talk about modern applications and the requirements of modern applications and what is so-called purpose-built databases. So what are the application requirements? What is a fully managed database service? What does it entail? What's your responsibility? What's the Amazon Web Services responsibility? Why should you even care about purpose-built databases? And how should you choose the correct database for the job that you're doing? So this is actually a very interesting time to talk about this topic because we have been talking about the data growth and how it drives innovation and how much data we are collecting. But I would say that during this year, it's becoming much more obvious with the growth of generative AI, AI and ML products. So we have a lot of data and the data growth is still going on. But now we actually have tools that are very good in pulling data from different sources. And one of the major sources is the database environments. So if you look at the explosion of data grows tenfold every 5 years. We talked about last time when we talked about the serverless side, so the microservices and the event-driven architectures. So it actually changes the way we look at data. So remember when we were talking about the way we organize it. So what is going to be the triggering event to kick off any action? Where is the storage? So if you place the storage in the middle, and then you have the actual actions or microservices that will execute things for you. And of course, the fact that we are seeing faster pace of innovation and rate of change than ever before. So it can be also be seen stressful, but certain things and certain practices, so let's say when you talk about databases, will remain that the way that they have been. So if you understand databases well, you can implement that in multiple different database types and releases. So the question is, what is a modern application? So basically, when we look back to last session or the immersion day and also the serverless session, it is basically decoupled applications. So highly distributed, decoupled applications, and how to enable developers to build those kinds of applications using different services. And you remember that there are multiple services, over 250 services in the Amazon Web Services stack. How do you do that so that it scales and it's performant and it's also manageable? So if you look at the exam itself that you're planning to take, the practitioner exam, there will be questions like, what is a modern application? So decoupling the application, having those microservices, making them scale even on a global level. And also, how do you secure those application environments? So before we actually dive into the databases, it's good to keep in mind that the application architectures and patterns have evolved. So you might see in the exam phase, you might see questions like, what are the typical architecture patterns and how they relate to, for example, databases? So what has changed? So if you go from the original, very monolithic mainframe environments, we have gotten into client-server type of environments where client uses a server directly. We have moved on to three-tier application models, so having those different layers. And now what we are looking at today, we are looking at the microservices. So we are basically breaking the monolith architecture into smaller pieces. So the question is, why is this? And why should you care when you actually plan to do a database design or even choose which kind of database you should be using? So there's quite a lot of application requirements. So the fact is that the modern application requirements require much more performance and scale and availability. So if you look at if you're building a startup environment, let's say you have the best idea for a multiplayer game, you might end up having users in the millions. So the biggest multiplayer games might have hundreds of millions of players. So the user growth is also immense. The data volume as such is growing, so going from terabytes to petabytes. And locality can be global. So let's say that if you have that one-hit game, it might mean that everybody's playing it across the world. When it becomes the performance topic, so there are microsecond latency rather than millisecond latency expected. And you might have request rates that go up to millions per second. So you might have also users that use different platforms. So having the mobile devices, let's say you have sensors that you will be using, different kinds of laptops, operating systems, etc., etc. So basically the scale is virtually unlimited. So the economics in order to thrive in this kind of environment has to be pay as you go, because if you would be paying for the maximum that it might get to, you would run out of money before you begin. So a few things about modern application requirements. Everything should be an API, so there should be an instance API access in order to access the environments and infra, and also decoupling the components out of the monolithic application approach. So we are going to talk about purpose-built tools, and today it's going to be about purpose-built databases. So developers, if you look at the developers' responsibility, so developers are going to do what they are doing the best. So how to break a complex application into smaller pieces and also pick the right tools to solve those problems. So this allows you to have applications that are well architected and also scale. So most of the developers are now building highly distributed applications. And you will see a lot of databases. And one of the challenging part of this topic today is that if I just throw all the databases at you, you will go away and say like, oh, that's crazy. I don't want to touch that. So you have to have some kind of mind map, what relates to what. And I will give you a few examples on that during this day. So you will have a couple of examples, also a couple of real examples of how different vendors have chosen their databases. But let's take the example of us. So let's take Amazon as an example. And let's look at the databases of Amazon. So Amazon has taken on petabytes of data. So the actual retail site has tons and tons of data. And it has been internally stored in different kinds of databases. And we are going to talk about the database history a bit. So I will share about the history and the timeline in a moment. But given the fact that has been like the typical layout for this industry, it has been a lot about relational databases. It has been quite monolithic in many ways. And we had about 75 petabytes of internal data stored across 7,500 different relational databases, mainly Oracle. And that was actually split to different purpose-built databases. So that data mass of that 75 petabytes was actually migrated to different types of databases. And that was done also without downtime. So what does the downtime mean? So let's take a site like Amazon.com. It has to be online 24/7. That's the expectation. So people are shopping all around the world, around the clock. So in order to be also successful in a business, you have to be able to guarantee that you can do migrations of data and databases so that it won't interrupt business. So why did we do that? So why did we change the platform? Shouldn't we have just kept on using what we had? Is that one thing was cost. So we actually reduced the database cost of those 7,500 databases by about 60%. So cost is one thing. And also, you might have a scale, kind of a different scale if you're doing the same thing, if you're breaking a monolithic application. So you might have 60% saving. You might also see, and what's really typical is that even 90% savings. The second part, which is much more critical than even the money, is the performance improvement. So when we chose purpose-built databases, our latency of our consumer-facing or customer-facing, so the shopper-facing applications was reduced significantly. So it was actually reduced by 40%. So performance is a huge factor why we changed the database landscape. And of course, the fact that you might have an administrative overhead. So when we switch to different types of services that require less of managerial access and admin access, it cuts down the admin access cost. And for us, it was about 70% during that phase while we switched to different architectures. So it also gave the teams a bit more freedom to choose what they want to use and why they are using it, based on, of course, those factors of cost, performance, and also the administrative overhead. So so think about that when we are talking about purpose-built databases, and I'm going to share you a couple of examples, but let's talk about the database and the database history so that you get an understanding, if you're not familiar with what is perceived as databases and how long is the history of databases. I'm not going to spend too much time on this, but just a glimpse on the history. So the timeline is actually quite vast. So it starts from, actually, we can go beyond 1920s, and then we started having different types of databases. And what's typically seen as a database is something that looks like a table. So you might have something like an Excel file type of layout. So you have columns, you have rows, you have cells of data, and you're storing data for some purpose. And that timeline, now that we are here, now that we are during today talking about this topic, has actually accelerated extremely quickly. So let's ask ourselves, like, why are we storing data in the first place? So what is the purpose for any database environment, or what is the traditional database environment for any company, any enterprise? So it might be something like this. So you might have a central or centralized databases. So you might have one or multiple, and you have multiple purposes for storing that data. So traditional database landscape for a very typical business could be like you have the orders database, so that's the customer orders. Let's say you have a booking database for customer bookings, payments processing, so basically the financial side. You might have an inventory of products. And then on the other hand side, you might see things like analytics. So how do you look at the financial figures? And how do you report on those financial figures? And how do you do, for example, invoicing? So that's a very typical landscape. But the thing is, you could do this with multiple different products. And what I'm trying to do today is categorize or give you a mind map of those products, but still keep you intact with the most typical services that you will be facing. So even though there's a vast list of things that you could be doing, there's a likelihood that there are some things over the others that will be much more typical. So my career has been around relational databases, like most of my career. And the scale has been from teeny tiny databases to global databases, and also extreme availability databases that have very, very specific requirements. So let's take a few examples. Let's take a global bank, global banking infra. How they use databases is different than your typical gaming customer. Or let's take a healthcare industry provider, like hospital environment. They are incredibly critical. They have to have an uptime that they can predict. They might have the possibility to take downtime at some point, but in essence, it is a critical infra that has to be live 24/7, and any downtime will have to be predictable. So you see that there are nuances with how the databases are built, but majority of them, what we are seeing today, has been around relational database theory. And that is the reason I'm going to start off by talking about just a short chapter on relational database model. And by saying this, when I said I have been working with this area most of my life, this part is evolving. And now we are looking at, could we build it differently? Could we actually gain some benefits of not using relational databases? So let's take a short example of what is a typical relational database model. So like I said, regardless if we're looking at the beginning of 1900, so if we are looking at the beginning of 2000, we have been looking at data as tables very typically. So when it comes to relational databases, we have something called relational database model. So we have groups of data. For example, we might have like production data as you have in front of you, products, customers, employees, product lines, shippers, etc. Tables are called relations in relational database model. And it's based on mathematics, so it's based on set theory. You have rows that can be also named differently, so you can talk about tuples. You have columns which are called attributes in the theory. So the data itself that is placed in the columns and rows has different theories behind it, how relational database is built. So we talk about, for example, domains. So domain might be a list of acceptable values, so atomic values like weekdays. So we know that we have a limited number of weekdays. So we have that list that we can say we can go through Monday, Tuesday, Wednesday, and we know that list. So there's no question if there would be like a surprise element there. So that's a very good example of data that fits very well in a relational database model. Rows, we can have a lot of them, but the expectation in originally relational database model was that we wouldn't have to repeat the data very often, but that's not the case. So data does repeat, and there are certain elements that do repeat. The model itself as mathematics is really interesting. It also talks about things like how to handle missing data. So we have things like outliers of null. So null means the value doesn't exist. So null is actually one of my favorite topics when it comes to relational database theory, because when it relates to this theory, even though it does exist in the databases, the theory doesn't apply that well. So null is difficult because null can be compared because we don't know why the data doesn't exist. So you can only determine if the label is null, so the data doesn't exist, or it exists, so there is data. But it's not comparable, and it also affects the way that we do any kind of algorithmic approach on the data. So when you look at those topics like customers, products, employees, product lines, and such, you see that there are lines going across from table to table or relation to relation. Those are called relationships. So how do you actually attach different areas together that have different sets of data? So how do you actually say that we have products that belong to product lines? Can a product belong to multiple product lines, etc.? So this is a very typical way of approaching databases. And this has been also based on science, and it has been written about a lot. So for the past decades, there has been a lot of scientific writing also about this. There's also writing about how should you approach the language that is used to query the data. So how do you create those tables, relations? How do you manipulate those? So how do you add data and remove data, etc.? And how do you actually do the part of data control? So let's say granting somebody access to tables or revoking those accesses to tables. So it's fair to say that relational databases will not disappear from our lives, just due to the fact that it's probably the most studied area of data storage. But it does have its own challenges, and we will talk about those too. So, but it's very much formalized. And wanted to mention that there are a few people that can be seen as founding fathers of relational database, and those are Ted Code and Chris Date, who have been doing basically their whole life's work worth of relational database theory. But okay, so we could just dive in and talk about relational databases, but why don't we? So why would we not talk about just relational databases? The reason is that the landscape is now evolving really heavily. And if I go back to the slide where you see the relational database model of tables and concepts, that's cool, but it does have its challenges. So it does have challenges of it doesn't fit all purposes that we are trying to use it for. And also in the past, we have seen the landscape evolve in ways of there are databases that will disappear from that landscape. So let me first try to give you a list of databases of how I actually categorize them in my head. And keep in mind, not everybody shares my opinion on this. So I would actually, if I would just prep for the theory part, I would say if I look at the whole landscape and look at the whole 1900s onward, I would say that the database types as are perceived right now are starting from hierarchical databases, and that is like a precursor to relational databases. So what's the difference with hierarchical databases and relational databases? So hierarchical used to be databases that had very tree-like structure. So you had like main, and then you have children, and that's basically it. There was no more structure. What's the difference when we went to relational databases? The difference is that relational database theory is much more based on math and the rules of math and how the algorithmic approach is done. So there are also rules around how the data atomicity and manipulation has to be done. And it's much more formal, and you can rely much more on if you have multi-users, so you have multiple users using databases, how they access and how they see the latest data, and how we guarantee that they always see the latest data. That was not the case with hierarchical databases. So it had a lot of multi-user challenges, and that was the reason it actually got, we still see some hierarchical databases, but they are not much there anymore. So they got moved out by relational databases that has been the de facto standard for the industry. But okay, so what about after relational? So some relational databases, and there we talk about databases that are key value or can be graph, column family, time series, etc., etc. So what is the fundamental difference based on like the relational databases and NoSQL databases is that the structure is much more flexible of how we actually implement data. So let's say that I'm taking order processing or I'm doing a multiplayer game. The amount of data that goes into, let's say, the multiplayer game session, or let's say the order processing, can be different based on the customer that we are handling. So it doesn't have to fit the same scenario as a relational database model. So going back to the slide of relational database model, when you have your customer and you have your orders of products, you have very fixed things that you have in the table and in the columns, and it has to fit that schema model that you have. What's the difference when we go to more NoSQL databases is the fact that it's much more flexible. You will hear debate when you have people who have worked all their careers with relational databases saying like, that's the wrong way to do it. The thing is, in some cases, it's much more performant way of doing it when it's more flexible. I know that people are adding a new SQL databases category, and it's a bit questionable if it does exist, but let's talk about it a bit. So new SQL databases are kind of multi-model type of databases that you see approaches combined with hybrids of relational databases, NoSQL, non-relational, all kinds of models combined that take the best features of both all the worlds that they are trying to implement. So I would say like that is the mind map of how I see those categories. And then you see a number 5 that has an asterisk in front of it. You see a lot of talk about in-memory databases, neural networks, object-oriented, etc. Those are all approaches that can be found in relational databases, in NoSQL and NewSQL. So for example, if you look at the object-oriented programming languages, you might see their features being implemented in relational databases, in NoSQL databases, and NewSQL. In-memory being how do you raise certain structures of databases in memory so that they are fast accessible. That's also something that is found in all the database types that are currently being used in the industry. So that would be my kind of mind model and mind map. So how about the exam? So what is typical that you would see in the practitioner exam? So first of all, you will not hear questions around hierarchical databases because they have basically been retired. Relational databases will be a hit where somebody might say that as a practitioner, you have to introduce a relational database to your customer, and then you need to know whether the product is relational or not. Same thing goes for NoSQL or non-relational. You might see an exam question when they say the customer wants to use a key value data store, and then you can be certain that it's not relational. Then you need to know which services on AWS are key value. So look at those keywords that you see in the exam. Those will be really valuable when you're answering the question. So very often when you see, for example, the key value, you can look at the answer options, and if everything else is relational and you see, let's say, DynamoDB, then you can go ahead and say, oh, that's the one. So it won't be very complex what you see in the exam, but you need to understand the categorization at least. A couple of things that we are seeing as trends when it comes to customer cases is that customers are also, besides looking at what types of databases they are using, they are looking at how manageable those databases are. So we could say that many of the customers we are talking to today are looking at moving to fully managed database services. So developers want to use them because it's less overhead for administration, and they can be much more easily decoupled. And then, of course, how do you manage, how do you use your time of your team? So, for example, if you have a vast team, you don't probably want to spend too much time looking at the backup scripts and tuning them. You probably would want them to be working out of the box. So fully managed database services is something that is very much on the radar and has been on the radar for the past years already. So if we look at the old guard commercial databases, so mainly the relational databases hit this category. And then we have the relational databases that are evolving much more into the fully managed database service category. Why are people so critical about them? So one of the things is that they can be very expensive due to licensing, for example, or let's say support agreements. There's a lot of vendor lock-in. So let's say that if you're using a specific relational database product, you might be using specific language to create the procedural code, doing the tuning. It takes a long time to educate people on different products. And yeah, so there's a lot of reasons why they are also seen as tedious. So what does fully managed mean then, regardless if it's relational or NoSQL or non-relational? So it means that we are now providing much more self-managing databases and also like the analytic services. So things like hardware software installation, well, naturally you won't be doing the hardware installation when it's the cloud, but in some cases you don't also need to do the software installation. in many cases, the software is already installed and also performance tuned for you. So the configuration is done. And you can also automate certain things like patching and deciding what kind of patches are automated. And of course, backups is one of the areas that is seen as time consuming when it comes to the old type of environments. When it comes to performance tuning and high availability, the more you can automate and the more you can have fully managed like automation for a database, the more time you have to use on the actual development. And then things like capacity planning and scaling, let's say databases or database clusters, and how do you scale like compute and storage. So there's a lot of areas that can be automated, but then the question is, what is automated and what is seen as self-managed when you compare databases on AWS? So let's look at that. So fully managed services on AWS could look like something like this. So if you look at what is self-managed, so regardless if you're doing it on-premise or if you're doing it on your laptop at your home, or let's say that you're installing your own managed EC2 instance and doing it all yourself. So the stack that is self-managed is basically everything. So you need to do all and everything that includes the best practices. So doing the documentation reading, routine maintenance, monitoring, patching, scaling, compliance, security, backup, etc. But okay, so let's say that we take a managed database from the cloud. What is given to us automatically and what do we need to take care of? So on AWS's side, what we see that is a fully managed database is that, of course, we are using the best practices and we're also documenting them. We have certain routine maintenance that is, of course, included in the infrastructure maintenance. We have monitoring in place. So we have talked about CloudWatch. So CloudWatch being the centralized hub for getting your log files and pulling data out of those, or let's say CloudTrail that allows you to also audit who did what type of activities. So things like automated patching, so smaller patches that won't cause downtime can be fully automated when it comes to fully managed services. Or let's say that you want to scale your environment. So you notice that, let's say your multiplayer game that you have with your startup is gaining traction. You can do so-called push button scaling. So saying that we want to go from class to class in different environments, standards. And of course, compliance, how compliance is managed. So industry compliance. So for example, let's take GDPR. Let's take any of the like the HIPAA payment card industry standards. How those are managed are already documented by AWS. And we also have the documentation. What is the expectation for the customer to take care of? Isolation and security. Remember that security is a shared responsibility, and this is a question that you might end up seeing in the exam. So shared security model, what do you have to take care of as a customer and not what AWS is taking care? And then, of course, backup and recovery models and automatic failover scenarios. So, okay, so what's left for the customer or the developer to take care of when it's a fully managed database environment or fully managed service? So, of course, anything that you do with schema, so going back to the relational database model, so planning out your tables, rows, columns, how do you manage the data, what do you collect or don't collect, that is up to you. Also, how do you query that data when you're a developer? How do you want to query that? And also, fundamentally, if you want to do specific optimization based on that data, of course, that's based on how do you develop that application. Query optimization partly is a shared responsibility, but mainly if you're talking about developer responsibility, the query optimization falls underneath the customer responsibilities. So that's cool. But let's look at then what are the options or like what's typically seen as database types in the AWS side. And one of my worries is when I share I have one slide coming up that has all the databases. So somebody's going to run away at that point and say like, no, not doing this today. Don't worry, there are only a few databases that you really need to understand what they do or and what they are good for, and also what would be the reason not to use something. So I love the quote from Werner Vogel's Amazon CTO, who says one size fits all database basically doesn't fit anyone. So when we are looking at distributed and highly distributed environments and modern microservices environments, there is no such thing as just one database that would fit everybody. So keep that in mind when we talk about this. And when we start talking about the purpose-built database, there are a few things. So there's scale, there's performance and availability. So for some decades already, the relational database was the choice to have. So no matter the shape or the function or the application that you were doing, you would probably build it on relational databases. There was no real other options. So it was driven through the data model and the application use case. You might model it differently, but that was the de facto standard. And of course, you had your ways of normalizing your data schemas and having the referential integrities and doing all kind of performance tuning. And they are still absolutely like key points what we need to talk about. But now that we are building highly distributed and decoupled applications, we can use certain cloud native databases. So I'm going to show you the slide that I said that somebody was going to run away when you see this. So keep in mind what you see in the next slide. You don't need to know them all in order to get to your practitioner exam. So I will show you a mind map of how we categorize purpose-built databases. And let's then look back to the fact of we have the relational, we have the non-relational, we have the maybe new SQL type of databases. So how they fall underneath that. So purpose-built databases. So you have columns of relational, you have key value, you have document, you have in-memory, graph, time series, ledger, and wide column. So instead of having like a huge list of different databases, so I could actually throw like a bunch of databases at you and say like there are hundreds of different databases you could use. This is more of a category exercise. So you can take relational as its own category. So many of the builders and developers understand relational systems, so we don't need to necessarily spend a lot of time here. But let's put it this way. If you have an application that requires a strong consistency model, where you have very fixed schemas of data, you may not be fully aware of all the questions or the single questions you will be asking from the data or the data set. But when you ask a question of that data, let's say, show me the customer's orders, you need to be really sure that the single question that you're getting for the answer, it has to be consistent. So consistent meaning that it doesn't change based on the time of the day if the data hasn't changed, or the fact that how many users you have online. So the relation is usually a good fit for that. And the thing is, even on the relational category, you have a lot of options of how to build that on AWS. And we will go through those options. So I will go through the main options with you. And one of the main options that we will talk about is RDS, as you can see on the slide underneath the relational. And you have Amazon Aurora, which is very Amazon-specific way of approaching relational databases. You will have all the big players that you have seen in relational databases across the history. So you will have your Oracles, you will have your options to have your DB2s, you have your SQL servers, smaller databases, MySQL, MariaDB. So there's a bunch of database products that fall underneath that category. So so if you look at the way that we develop applications, and if you actually think about when would you use key value or NoSQL type of databases, and this is a category you do need to understand, and you need to understand the difference when you go into your exam, is think about how you build databases. So if you look at the key value category, you might see things like the most typical one is the DynamoDB. And that type of database, of key value database, optimizes the running key value pairs that you have from your data. And it actually provides you with much more lower latency. So you can get to single-digit millisecond latencies with that type of database product. The schema or the way that you handle the data is much more flexible. But the expectation is also that the group of data being put in or returned is much smaller than maybe your traditional relational database model. So one DynamoDB table can have one item to trillions of items, and it will perform the same. So it's optimized for the key value pair management. And there's so many companies that are using it. So there's a lot of gaming companies. Let's take example of Fortnite. Fortnite is using DynamoDB for their processing, and they scale that and really love that product. And it scales better than any of the relational database products, but keep in mind there are limitations where it doesn't fit the purpose, when you always have the limitation of what needs to be returned and is it a very fixed model of organizing your data. So then you see other categories, and I'm thinking about, I may not spend too much time on the other categories. There are things that I might mention to you, but many of the categories that you see here might have the same fundamental things as relational and key value. So you might actually see document databases, somebody might pop them under the key value databases because they are fundamentally much more typically key value databases, not in all the cases. Or let's say in memory, when you raise memory structures, so that you have everything running in memory, so nothing will be returned from the disk, it will be running on memory, which is much more expensive, of course. You can place in memory in front of relational and key value. So the question is, do you need to know all this when you go into the exam? And the answer is no, you don't need to know all of the categories, but you do need to know the difference between relational and key value pairs. There are some kind of spin-offs that I can mention, and I will do them in the prep also when we do the exam prep. And there are things like ledger database. And ledger database is something that might pop up in the exam. You might see that. And the question is, why is that? And ledger is popping up there because it relates to how to guarantee that the data doesn't change. So how to guarantee like a cryptographic way of keeping the data intact so that we can guarantee that we know the data's history and we know that it hasn't changed. And you have a whole lot of products that does the ledger database. In our case, you see QLDB underneath there, but you will see that with all the big vendors, they are doing some kind of version of ledger database. So many organizations build applications that have ledger-like functionalities because they want to know the history of the data. They want to know, let's say, if it's a payment processing thing, they want to know that what happened with the banking transactions and guarantee it's not changed throughout the history or when it's moved throughout the network. So then you need the cryptographic comparison algorithms that you know that it stays intact. So for Amazon, we have built QLDB, which is a fully managed version of the ledger database that has immutability. So the data doesn't change, and it has a cryptographic verifiable transactional log. So that is a very specific use case. So the only thing you might have to know during the exam is that if somebody pops the ledger database on the table and asks what are the benefits, it's the immutability, and it's the fact that you can have cryptographic algorithms to ensure that data has not been changed. Other than that, I would say that there are tips and tricks I can share when we do the exam prep when it comes to databases. But today we are going to talk about mainly about relational. We are going to talk about the key value. And then let's look at maybe like a really short example on that I can show you like what I use for practicing with teams when we build databases. I wanted to take like a customer example, talk you through like why customers choose something. So once they start building on AWS, you might use those categories and think about what works and what doesn't. So let's take something that everybody knows. Let's take Airbnb as an example. So let's take Airbnb. They talk about a lot using database that are purpose-built. And they have very typical things that they do with their data. So they have a user search, they have a session state, and they have, of course, your traditional relational data. So if you look at the Airbnb and how they behave with their data, they have user search that also relates to how the user has searched data in the history. So they have like a massive data volume of Ursula going through like Airbnb and looking at, oh, I would like to go there. And then it might suggest like, hey, are you still thinking about traveling to Rome? We have a really nice suggestion for you based on what we know about you, what you have rented before, and based on what you have searched for. So, but that search and that capability has to be fast. So, and it also has to be flexible when it comes to the data that we are collecting. So your traditional relational database model doesn't actually fit that purpose that well. So that is the reason Airbnb actually chose to use NoSQL non-relational databases for that. So they are using Amazon DynamoDB, and we're talking about that product very soon here. So the fact is massive data volume. The size of one transaction is not much, and they need to be able to do quick lookups of personalized search. That's cool. Okay, what about session state? Session state means that how do you cache information so that it's flexibly and fast available, basically in memory, and we are talking about microsecond latencies. So we're talking about always sub-millisecond, microsecond latencies to render the site and show the customers the latest information and keep them also engaged with the product. So we have different session state databases. One of them is Amazon Elasticache, but there are a lot more. You don't need to know all of them in order to take your practitioner exam. If you're doing data engineer, which is an associate exam, then you need to know the differences. And then, of course, they do have a lot of relational data. So relational data meaning that you have to have the referential integrity, meaning that you know how different rentals are located. So let's say location and rental are based on map data, and they have a referential integrity so that we know where they are placed, and we will always get the same end result. And they do have a primary transactional database that is based on Amazon RDS. So that is our fully managed relational database service products. So let's say this is a very typical example of what you would need to understand why something is chosen and why something is not chosen as a database product. So I'm going to spend a bit of time. Let me have a look at the time so that I will not spend too much time so that we'll get through all the necessary ones. So I will take on the main services as we have them in this category. So relational, key value, and then we might have a couple of outliers. So one of the key products that you need to understand is the Amazon Relational Database Service. Let's look at it and let's see what we need to know about it. So Relational Database Service on Amazon includes a lot of different products. It has over 14 years of history. It uses a lot of security best practices. There's a lot of innovation that has gone into the actual management part or the automated management part of the RDS product. So it removes a lot of tasks that normally your normal database administrator would do. So there's a lot of automation for backups, recovery, and different kinds of like replication services if you want to replicate your databases. Also, how do you build high availability and durability into the cloud environment? So it is fully managed service offering. It's quite simple to set up and also operate and scale. So it was launched in 2009. And yeah, there's a lot of operational excellence that goes into that. Maybe for the industry understanding, it's a good idea to also mention that starting from 2022, Gartner started recognizing RDS with the industry's highest rating in the solution scorecard. So as a database platform, as a service. So it's also something that really determines how RDS measures against anybody else's offering. So the criteria is basically required, preferred, optional criteria. So we met 100% of the required criteria. So it's one of the highest achieving managed database environments. So what are the deployment options? So what's included? So we know that it's relational and we know that it's fully managed. So you can actually deploy something, and you remember we talked about this in our first sessions, you can deploy something by either using the console, so you can log on to your console and deploy a database, but you can always also call the API. So everything is an API when it comes to AWS. So you can run it as an API call, you can do a command line interface script that will deploy the same thing. Everything, all of those options are always available. So you can basically decide to go and deploy a database by clicking on the console and saying, I want to deploy an RDS database. But you have multiple choices over there. So you have multiple database engine options. So you can have engines like Amazon Aurora, which has MySQL compatibility. Or let's say you have PostgreSQL and PostgreSQL compatibility, or MariaDB, or just pure MySQL, or pure Postgres. You have Oracle, you have SQL Server, and all of them have certain service-specific offerings, and also maybe in some cases limitations and changes how they do, for example, certain security features. Those security features or offerings will not be asked in the practitioner test. So there are a few ways of deploying your RDS environment. So you can choose by doing a so-called custom approach, which means that you get platform that you have a bit more access to the platform side, so the OS side, or then you can do fully managed, so which is the basic way of deploying RDS. And then the expectation is that you don't need any platform access. So you don't need to access, let's say, settings on a Linux kernel level or something. So the more managed you get, the less overhead of the administrative tasks you will have. So of course, you could also have the fact that you don't want to do fully managed. So somebody was asking a question at some point that can you have databases outside the fully managed way of approaching it? Yes, absolutely. So anything that you have done in the past with EC2 instances, you can also do with database products. So let's say that you have a database that is not supported by RDS, you could actually place it on an EC2 instance and manage it yourself. So you can do everything that you could do with the Linux box with EC2 instances and do any customization that you want. So the key things you need to remember about RDS is it's fully managed. It provides you with multiple different engines. You need to choose the flavor that suits you. Then there's an area that is, I know that I mentioned it also when I talked about RDS, but it's also very specific to Amazon. And that is a product called Amazon Aurora. So this is a topic that will pop up in the exam, not in a deep level, but you need to understand what is the difference if you would choose Amazon Aurora. So a couple of things. This is a relational database. So in any case, when they talk about Aurora, it will always be relational. So the question cannot relate to things like key value, NoSQL databases. So let's look at Amazon Aurora a bit. So it has a couple of flavors. So it has flavors of being MySQL or PostgreSQL compatible relational databases. It is specifically built for the cloud. So there are things like performance and availability that is much more different than many of the other ways of approaching this. And what is really unique about it is that it's about 1/10 of the cost of running any commercial grade databases like the big Oracle DB2 SQL Server databases, because of the fact that it cuts away the licensing and the support fees. So you get performance and scalability, so basically 5-fold throughput of a standard MySQL, and also 3-fold of standard Postgres. And you have different scale out methods. So how do you scale out your database environment, adding more nodes to the environment? So talking about more like a clustered environment approach, having replicas, and how those replicas can be placed in different availability zones. There's availability and durability category. So how do you do fault tolerant and self-healing? So there's a very interesting storage, and I will show you a couple of pictures, but remember when I show you the pictures about the storage options, you don't need to go or dive as deep as this for the exam in order to pass your exam, but it's good to know. So there's a capability that allows you to do self-healing if there's some kind of level of corruption seen. And also, how do you keep up your backup so that you would not lose any data, or at least if you would lose any data, you always know that the data loss is in very short amount. So we are talking about like 60 seconds or something. So what kind of backup operations will happen behind the scenes when you're using Aurora? There's network isolation when it comes to securing the environment, and of course the fact that it's also falls under the category of fully managed databases. So it's managed by RDS, so very similar setting as RDS, but there are certain flavors that are not provided by the RDS for all the database flavored provided by RDS. So let's look at it a bit and let's see what are the limitations. So couple of things to mention outside the fact that it's like automated, fully managed. So all the things that the RDS side does already. So any provisioning, database setup, or patching can be automated. I would highlight maybe the fault tolerance side and self-healing side, and also the fact that it auto scales to 64 terabytes per instance if you need to scale to those amounts of data. So let's look at the architecture a bit. So we have, if we dig into the Aurora environment, I mentioned that it's compatible. You can choose the compatibility, either MySQL or Postgres. We have changed certain architecture features. So you could say that it's MySQL and Postgres on steroids. So you will see much more performant environment than you would have with your out-of-the-box MySQL or Postgres. So we have done something that it's not completely unique when you look at databases. So I know that there are companies doing similar things, but we have separated the compute and storage layers. So we have the nodes on top of the compute layer, and that's the query processing side. So seeing that you have your primary node, your replica nodes on top there with blue color. So that is the side that will process your SQL, your transactions, your caching. And you can have multiple of those. It scales to 15 nodes. And if you look at the underside, which is the shared storage volume, so we separate it in ways that the storage layer now here on green is purpose-built for the actual distributed storage system. So it spans over, so it's a multi-tenant and it spans over hundreds of storage nodes distributed when you look at a region. So you have a region that consists of availability zones that we have talked about. Those nodes, those storage nodes span over 3 different availability zones, meaning that it will make your data highly persistent, highly scalable. So you have multiple copies of the data also available. So you can think of the availability zone when it comes to the Aurora as a fault isolated data center. So Aurora always splits the data in 10 gigabyte chunks. So each chunk of those 10 gigs is copied 6 times with 2 copies in each availability zone. And that is one of the fundamental pieces of being able to be extremely fault tolerant, being able to recover from any kind of, let's say that you will see a corruption type of setting happening, that you can always recover from those. And it's also extremely performant and flexible. So why should you care? So you should care because of the reliability. So if you would lose anything like a data center, which would be very highly unlikely, you would always be able to recover your database. So there's numerous innovations that go into that. And of course, the way that the storage is tribe across the volumes and such. So all the primary replicas and such that you have in your Aurora database environment point to the same storage, but it's also availability zone wise. So there's also preferences how it pulls the storage from the closest location, how it recovers from different scenarios. And like I said, you can add up to 15 read replicas. So you can have on top of the same storage, you can have your primary and you can have 15 read replicas. So that is one of the things that the customers really love about the Aurora, because you can also use those replicas not only to recover, but you can use them to offload certain things. So you can offload your reporting applications to read from read replicas. You don't have to point them to a primary if you don't need anything else except read access. And yeah, so typically the replicas, I get a question around, like, do you see a lag when you have those multiple replicas running? Let's say you have one primary and 15 replicas. Not really. So a typical lag that you would see between those replicas would be between 20 to 30 milliseconds due to the shared storage model that we have, because the storage is also syncing behind the scenes using the Amazon Web Services infra across the availability zones going across the black fiber network. So it's extremely performant. So what's the difference then if you look at this one? So the Amazon Aurora and the split architecture of having those compute nodes, having those storage nodes. And then if you look at the RDS, so let's look at the differences. So basically everything that you get from RDS is already included in Amazon Aurora. So things that you have to think about when you look at having your databases on premise, or let's say you're running your database on your laptop when you're a developer testing out something, or having your database on an EC2 instance in the cloud, and then having your Amazon RDS. So what is the difference? The difference is basically as boring as it sounds, moving to a managed database like Aurora or any of the RDS flavors is that you can do things faster. And you know that certain best practices are already implemented for you. On premises, you will cover it all yourself, or you have teams who will cover certain areas. And so basically moving over to EC2 instances will allow you to get the server maintenance, rack stack, etc., power, cooling, etc., will be taken care of for you, but it will still take care of the patching, software installation, any of the high availability stuff, and RDS does most of the stuff for you. So you will only focus on your data and optimizing your application. So what is cool about also the Aurora and what is specific about the Aurora that might pop up also in the exam is that, yeah, the storage is auto-managed across 3 availability zones. It auto-scales by using the 10 gig increments. So you don't have to pre-provision anything. So let's say that you are starting your amazing startup and having that really cool game that's growing and growing. So you don't have to start by scaling it manually. It will scale for you. So you don't pre-provision anything. So you will pay for only what you use. So that saves you time and effort. And it avoids you for the downtime of scaling your storage, which is also very significant when you look at databases. There's the continuous incremental backups, like mentioned, that is happening underneath the scenes. The only thing as a owner of the data owner, database owner, you need to know is how far back do you want to go? So how far back do you need to recover if you need to recover something? And this could be for logical reasons or like human error. So let's say somebody drops something or deletes something that shouldn't be deleted. How far back do you think you need to go in order to get and collect that data that you know that you're missing? And that's a decision that you have to think about. Amazon Aurora is unique that way, that because of the split between compute and storage, you can do storage snapshot which are instantaneous, and it doesn't affect the performance of the environments, which is really cool. So you can also store those snapshots indefinitely. So the storage layer itself handles a lot of stuff by doing automated recovery. So let's say that there would be a hardware failure, you wouldn't see it impacting you, and you don't have to worry about it. Let's take a couple of things that you might see in the exam that you might see questions on. So one is database backtrack, and this might be a question that you get through during your exam. And this is Aurora specific. So what is a backtrack and why should you care? Backtrack is like a rewind. So if you look at like your old videotapes or like anything that you could rewind is you want to rewind to a time you specify. So backtrack itself is not like a replacement for any kind of backup of your database or your database cluster, but it allows you to restore in point in time. So you have the way to go back to undo mistakes. So let's say that there's somebody who has performed a destructive action. So somebody does a delete and forgets to use the where clause in SQL language, which means that it deletes everything. You can backtrack your database to a time before the destructive action happened with kind of a minimal interruption of your service. So you can do that quickly. And it basically what happens. So once you start backtracking your database, so restoring a database cluster to a point in time launches actually a new database cluster and restores it from backup data of the database cluster snapshots that we talked about. So that means that backtracking a DB cluster doesn't require for a new DB cluster to or the old DB cluster to be interrupted. So you can also do an exploration of the earlier changes, so the data changes, so you can actually see if you have the data that you were expecting to see. So that is quite critical. You can do like back and forth, so you can see like, no, that was not the point in time. Let me go back, let me check where is the change. And that doesn't interrupt your actual production. So that allows you much more flexibility. That's a feature. If you see this in exam, the main thing you should think about is that, okay, we are talking about Amazon Aurora. So this built-in feature is specific to Aurora. And like I said, it's not destructive, so you can go back and forth. What else is interesting when it comes to Aurora, and I'm thinking out loud here, is that one is zero downtime patching. What is interesting about zero downtime patching, and now I'm going to use a word that I don't actually like, is that a zero downtime patching, we call it CDP as a feature, uses best effort, and the word I don't like is the best effort. So while we patch the environment with the new patch level, it best effort basis tries to preserve the sessions and client connections without interruptions. Best effort meaning not always. So if the CDP, so zero downtime patching, is successful, all the sessions are preserved and database engine restarts while patching. So it actually is not seen as a downtime to the users. In case that's not functional or you can't use the CDP, then it will cause a downtime when you actually have to restart the engine. It is also very dependent on when you have Amazon Aurora on which version of compatible MySQL or Postgres you're using. So CDP is available in Aurora with MySQL 1.13, and it's compatible with MySQL 5.6 and later. So there are certain things that are not compatible with zero downtime patching. So zero downtime patching might pop up in the exam. Things that you need to remember is not always fully zero downtime patching because it's the best effort basis. And that's basically a word that you might see in the exam. Then there's something called cloning. And cloning is cloning a database without copying data. So creation of a clone, like nearly instant or like real time. And so when you use database clone, you can basically cost effectively create clones of all databases within that Aurora database cluster. So typically a clone of database require like a minimal additional space when it's first creating. So it uses something called copy on write protocol. So data is copied at the time of the data changes. So either on the source database or the clone database. So you can make multiple clones of the database cluster, and you can have multiple clones made up of other clones. So you could have like a variety of use cases. Why would you care about cloning at all? So you might have something that you want to experiment with the data. So you want to experiment and assess the impact of changes such as schema changes or parameter group changes on a clone. That could be a use case. So basically clone a production database to run tests with real data. Let's say that you would like to try something like that would be like workload intensive, that would cause an impact on your primary database or your like non-clone database, doing like analytical queries. So those could be use cases for using cloning. And this is also specific to Amazon Aurora. Then we have a couple of more things, and then we are at the end of the Aurora part. And one is global database. So global database is a very specific use case, and keep in mind, most likely you will not see this too often. But we talked about database replicas when it comes to Amazon Aurora. So you can have, to primary, you can have 15 read replicas. So how about doing a global database? So let's start with the fact that we are fundamentally building a database of Amazon Aurora, having that one node, that primary node. So that primary node hosts your data. But what about if you want to extend to different regions? So you can have one master region, and then you can actually start adding regions to replicate to. So Aurora allows you to replicate data to secondary regions, and the latency to region replication is typically under a second. So when you issue write operations on that database, so you have that master, you have those regions, and you have the replication running, you point those write operations to the primary region, so the primary database instance. And the global database, what it does in the backend, you remember the split between compute and storage, it actually uses the infra behind the scenes to replicate your data, and leaving those database resources available entirely to serve your application workload. So you have a worldwide footprint, and you can have those instances in secondary regions as reader instances. So what's the benefit? The benefit is, of course, that you have a global replication that is quite fast. So remembering that typically under a second latency. So you can have that global approach. It's definitely something that you will think about if you are having like global services. So you can bring those data sets closer to the regional locations that they are read from. So the isolation is also great because that will protect you from any kind of failure that will happen throughout the region. That would be very, very disastrous event, but let's say that there would be like a worldwide crisis that would wipe out a specific geographic area. Your database would still be fully intact in the other regions that it was replicated to. So it brings you more availability. So that is a topic that you will see sometimes in the exam asking what database would allow you to do a global database infrastructure. If it's relational, it's most likely the global database of Amazon Aurora. You could do it with different relational database products too using RDS, but the automation as such that we have with Aurora is not there. So that is a piece of advice for the exam. There is a picture, and we will not spend a lot of time in this one. There's a picture about the physical replication, how it's carried out. So you have the primary region of Aurora cluster and how you have those 6 copies in 3 availability zones, and then how the replication server and the agent is replicating the data between the regions. Nobody will ask you a question on this during the exam. The only question you might see is a mention of global database, and then you need to be very careful to understand, is it a relational or non-relational use case? If it's a non-relational use case, you still have the global opportunity, and we'll talk about it in a moment. So the only thing I will mention about Aurora before we jump to the NoSQL part is that you will start seeing questions around Aurora serverless. And this is the only slide I will show about that. The interesting part of Aurora serverless is that it's all the things that we have now spoken about. It is on demand, it is auto-scaling, auto-healing. All the nice things about the shared distributed storage is still in there. So what is cool and impacts the cost is that the node part, so the processing part of your database environments, shuts down when it's not in use. So you can actually save money, and you can save significant amounts of money if you use this, for example, for your development environments to build them. So, and it also scales in a much more granular level. So typically when you scale Amazon Aurora, when you're adding those read replicas, for example, you will always scale out in certain chunks. This allows like 1.1, 1.2 type of scaling also for the instance level. So you don't always have to scale using full instances. And that will also impact the price. It impacts the price so much that typically you can see between 75 to 90% savings for those environments that are typically seen as good use cases, being like development environments where you would like to cut the cost of the front-end servers. So that is just a mention of this functionality. It is there. It's also fast evolving. You will not get deep dive technical questions on this. Next, I will spend a bit of time to talk about the NoSQL and the non-relational model. And I think that will be the last topic as technical topics that I will cover today. And then I might show you an example, if we have time, of what would be a typical use case of, let's say, converting from different database types to another, showing a couple of pictures of that. And then let's take a few questions. But in order to be able to also cover the questions on non-relational, let's talk about the most typical non-relational database that we have, and that's called Amazon DynamoDB. So that is a key value database service. So it's a key value and service for any scale. And one might think like, yeah, right, any scale, what do you mean? So any scale when the use case fits. So typically what we see with DynamoDB is that we have fairly smaller groups of data than what you see with relational databases. So it's very consistent. It's typically single-digit millisecond response time. So when you start seeing questions like you have small sets of data, or let's say you have high throughput, like processing product orders online for e-commerce, you need single-digit millisecond response times. Most typically, you're looking at a use case of key value. Not in all cases, but most cases. And it basically scales to any, it's kind of unlimited when you look at the throughput. So let's put it that way. DynamoDB is purely serverless. So when we talked about serverless last time, we talked about Lambda, we talked about SQS and things like that. This is also serverless. So there's no hardware to provision, no software patching, upgrades, etc. Scaling up and down or doing performance tuning is based on certain principles that you have, but it's serverless. So it also continuously backs up your data. And it has enterprise level security. And it integrates fully with the identity and access management. So DynamoDB is also a database product that you can scale to a global replication model. So keep in mind, if you see a global database popping up in the exam, have a think about what is the use case, because you need to understand, is it more non-relational or relational? So how do you easily replicate tables across multiple AWS regions? That is something that you can do also with DynamoDB. Very typical use cases, like mentioned, Airbnb was one of them. Lyft is one of them that is using a very heavy user of DynamoDB and non-relational databases. So there's a lot of use cases when you see very typical customers, also very traditional customers, reverting to DynamoDB because of its performance. So let's look at the available and durable concept. So DynamoDB is built for high durability, and it's designed to support 99.99 of availability. There's something called, when it comes to writes, it comes to three-way replication persisted to disk, so custom SSD disks, and read strongly or eventually consistent reads. So what you need to understand is that there are ways of doing the reads based on what is the use case. So when you do read operations, you can define, do we need strong consistency or eventual consistency? So meaning when the data changes are happening, what kind of consistency is expected of that data set of that given time? Data is always replicated when it comes to DynamoDB, same as Amazon Aurora, across 3 availability zones, making it high available. So even though nobody will ask you when you do the exam, it's a good idea to have a look at it. Let's say that we are doing the customer order. So you have your order ID, you have your customer ID, you see what they have ordered. So you have like a product category that we have been ordering. If you look at the 3-way replication of the 3 availability zones, when you put data in your customers orders table in DynamoDB, it's, hang on, come on. It's basically placed in partitions, and it's placed in multiple zones. So it has a very similar structure when you look at the Amazon Aurora, even though this is not your typical relational database model. It has the same copy of that data set in multiple availability zones in those partitions that it's hitting. So this is very similar to Aurora, even though the data model is different. What is also very similar to Aurora is the fact that you can have global tables. So let's say that you're building an application with globally dispersed users who have a lot of users coming across, let's say, Europe, Asia, North America. You can use the same table and replicate it over different regions. So that means that you have a highly distributed application that supports also the data on site, on location, and also having that low latency read and writes to locally available tables. So it's also disaster proof, same as Aurora. So it has multi-region redundancy in a case of something really catastrophic happening. It doesn't change the way that you develop your application, though. So it means that if your application is developed on DynamoDB, if you convert to a global table, you don't have to change your application. But what happens if you have a customer that says that all this is beautiful, we love DynamoDB, we love the global tables, that's very nice and cool, but we need microsecond latency. So the millisecond latency is not good enough. So then typically you will start seeing things like adding accelerators in front of your databases, and the accelerators are available for most of the flavors of the databases across Amazon Web Services. The most typical one of those accelerators that you will talk about and see throughout the exam is one that touches DynamoDB. Why is that? Because DynamoDB is already extremely performant. It gets that millisecond latency. In order to get to microsecond latency, you can add something called DynamoDB Accelerator. It's called DAX. So if you see DAX in your exam, think about high performance. It's also a fully managed service. It's a cache layer for DynamoDB. So it's even faster than what DynamoDB already is. So it provides you with microsecond latency. And that allows you to also scale to millions of requests per second. It is API like everything else on Amazon Web Services in an API. And it's typically, if you have to give a number in the exam, if somebody says that you have to deliver 10-fold performance improvement, it's most likely DAX. So from milliseconds to microseconds. So you can do millions of requests per second on a microsecond latency. So there's no heavy lifting to add that in-memory acceleration to your DynamoDB tables. There's not much as a developer that you have to think about. Like typically what you see with similar solutions, if you have relational databases, you might have developers thinking about in-cache invalidation type of scenarios, data population or cluster management. Those are usually not the case that you have to think about with DynamoDB Accelerator. It's pretty much transparent. So you can actually focus on building a great application. Really great question that I see often when I talk about this is that this is all beautiful. The global databases and the global tables and everything else is beautiful, but it probably does have a price tag attached. And there you would be right. So anything that you see here will increase the price, and the more users you have, so the more requests that you have, the price points get higher. So adding certain features will add to your cost based on the demand that is put on the database environment. So no changes to the database logic in order to benefit from DAX. So one of the questions, and then I will show you an example, and then I will take a bit more questions, is that when should I choose NoSQL versus SQL? So basically non-relational or key value versus relational. So let's start with a really simple example. So if you want to have the simplest database management possible, it's most likely non-relational, so key value pair. So if you want to use your application, so basically use your code to mainly manage the database integrity, in that scenario, most likely you will choose non-relational. So how about the other side? Do you need to do join operations? So let's take an example of join operations. I want to query my customer orders database by saying, show me customers all orders throughout the years that hit the category of garden products. So let's say we are doing that kind of query. That requires joins between the relations. So those relations and referential integrity is queried so that you will join data from different groups. That is typically done in a relational database setting. Because in DynamoDB, the table are much more seen as separate entities. And then if you would need to do integrity or those kind of constraints, you would need to do it programmatically, and it still wouldn't provide the same level of data integrity and acidity as relational database. So if you want your database engine to be responsible for your database integrity, keeping the data intact and managing those relations and relationships between tables, then most likely it's relational databases. And if your team already has a lot of SQL language skills, so SQL language skills can be, remember that's a standard. So SQL is a standard language that is defined by, it's basically defined by a science writing. Different vendors implement SQL a bit differently, but overall, if you write SQL language well, you can write it in any of the maturity environments. So that way, SQL language skills always means that then you might want to use relational databases if you don't have those performance things that you might actually look into the DynamoDB. So those are the main areas. So keeping in mind that once you're preparing for your exam, what do you need to know and what do you need to understand about purpose-built databases is that what category is the question in hand touching upon? So is it touching upon the relational databases, the key value databases? You might see different product names, then it might be a good idea to think about where does Aurora fit in? So keeping in mind that it's a relational database always. RDS, like the R in the front says, it's a relational database service. Or when you have DynamoDB. Then you have the outlier cases, and I will help you with those when we do exam prep. So you will see certain exam prep questions where you might see a question about the ledger databases. So immutability in database environments. But most likely the rest of the categories you don't see much of. So I was thinking I will show you an example before we stop with the slides. So let me stop sharing for a moment and I will reshare. And now hang on. All right. So now I should be able to reshare. So you should now see just the topic of saying cloud taxi scenario. So in order to understand the choosing of different database services better, let's take a short example of like invented customer. So let's say that we already have a customer that is using a database and they are thinking that they might be more performant on a different platform, or they might have to redesign something, or let's say they are just moving from on-premise to cloud. So let's see. So let's take like an imaginary rideshare application. And it's becoming popular and it's quite innovative in the way that they approach their customer-friendly features. They are now having an on-premise data center and they have a technology stack, which is a very traditional one. So they have a lot of Java, they have their web applications, they have very traditional client server, or let's say even 3-tier application model. They have an RDBMS, which is an Oracle database. They have certain challenges, and they have certain challenges that relates to databases and of course also cost. So let's see what those challenges could be. So the customer shares with us that they have challenges like high licensing cost. So they are paying a lot for the licensing. They might also have high support costs that are vendor specific. Then they mentioned that they have high operations complexity. So capacity planning, because they are on-prem, they need to do their hardware, purchases, renewals, etc. Provisioning new servers and managing the new servers. And one of the challenges is that they are not being able to scale quickly for peak demand. So let's say if their demand grows, they get a lot more customers. They can't match that demand. So in the worst scenario, the application itself gets quite stuck, it's quite crowded, and it doesn't work. So it's not a good customer experience that way. So let's say there's like a sporting event or any weekend or any party or something, there's a spike in taxi booking and they would have high demand, but they can't answer to that demand. Then they are facing also increased security and compliance and governance requirements, and they are planning to expand outside their region. So let's say that they are placed, if they are in the Nordics, if they are in Finland, they want to go to global markets. How could they do that? Because they are now providing those services out of their on-prem. And then they show us their cloud taxi data model. So the cloud taxi data model is also quite typical relational database model, as it is traditional database. So you have drivers and you have riders, which are the customers. You have different trips and you have payments and payment types and billing and car models and different kinds of rate codes. So that is all nice. So if we take those challenges and start thinking about what would we change if we would change anything. So let's take the key use cases that we see with those challenges. So we have the rider driver registration. So you have verification and validation. So who is a driver? So are they a validated driver? Are they a validated user? Authentication use cases. Or let's say that the customer wants to change their profile settings by using different car types, etc. Then you have the taxi booking and management. So how do I request for rides? How do I keep the spatial data intact, like GPS data tracking? So that is a live operation that is real time, of course, because the driver is getting to the ride requester. How do you map the drivers on the map to get to the destination the fastest? And how do you get the trip completion data? The challenge is that the weekends or the parties or the sport events will have a surge of traffic. And they have shared with us that the surge of traffic can be tenfold. So they would need to get to faster driver confirmation and mapping or geological tracking. So the real-time stuff should be faster. And they can't allow downtime for the application because that is basically their bread and butter, because they need to be able to cater to their audiences. There's also billing and payment processing. So how do you estimate the total billing amount per billing cycle? How do you do commissions, taxes? So all kinds of processing side of the financial data. And how do you make the payments to your drivers to keep your drivers also happy that they're making a living? So there's a lot of stuff like reference data, batch processing, acidity. When you see acidity, you have to think about that that is very traditionally one of the key focus areas in relational databases. So that might be something that we need to see if we can use something else for that. And then you have, of course, the analytical side. So how do you do like periodic reports, and how do you do downstream, upstream feeds for analytics, etc. So let's play around by introducing the idea that when we move them to the cloud, we would use something else to support at least some of the functionalities than relational databases. So the question would be, why would a key value pair or non-relational database be a good fit for this use case? So some of the key advantages that you typically see is that traditional SQL or databases have a lot of, it has a very lot of gain with scaling up the databases. So adding more bang to the server is a very traditional way of scaling your databases. You still do have relational databases that are clustered, so you can always do the scale out type of scenario too. We see a lot of features that could be key value lookups. So if you look at the use cases, they have like the actual requesting of rights and real-time processing. That is a very good match for that key value lookup, and quite small amounts of data that go through one single operation. Adding flexibility to the schema might be a good idea. So it might be a good idea to think about that the data payload might be different based on the user profile of the request. So you might go to a direction that is not so traditional relational. So what would be the benefits in this use case? Let's take a service overview. So service overview would mean DynamoDB, the performance side. So millisecond to microsecond latency. If you use DAX, you get the microsecond latency. So it can handle millions of requests per second, and it provides out-of-the-box microsecond latency. It does have global replication, but keep in mind, so does Aurora. So you have the option to do also global databases there. So serverless means that it's much more maintenance-free. So you don't have an infra that you have to handle yourself. It allows you to do auto-scaling, and on-demand capacity mode allows you to do scaling that will scale based on your performance requirements without having to do pre-provisioning. And of course, things like encryption at rest or on-demand backup and restore, but those are on both sides, relational and non-relational. And if you look at the performance at scale, it's about how to get the consistent low latency. So how to be able to answer to those requirements of those peak volumes and have a consistent low latency for your customers. So consistency is also key for the customer experience. So what we could do is actually remodel a bit. Come on. So how do you model for NoSQL? So understanding first the use case, what you're doing. So we are doing the right calling and also the GPS tracking. What are the access patterns that typically we require? Is it read heavy? Is it write heavy? Is it 50-50? What is it? What are the query dimensions and aggregations that you need to maybe able to do and cover? And how do you identify what are the primary keys that hold the information together? So for example, if you're a user of this service, Cloud Taxi service, what is the primary key? Let's say, is it your user ID that holds all the session data? What is it? And how that item will be inserted and read. So our use case is trip booking and management. So the request is by a rider, and there will be mapping of the driver for the request. Then there will be probably updates to trip information. That could be due to traffic. There could be a traffic block that will make changes to the trip information, and that has to be real time. And how do you query the trips by the rider, like what's happening and where is the driver, and seeing the real-time updates. And of course, the driver too. So how do you query those trips by the driver, understanding where the rider is, for example, the location, where do I find them? So what it could look like is that, first of all, in order to be a good fit for DynamoDB, is that there has to be some kind of key value access pattern. So that determines how the data is distributed. And you can have model of one-to-many relationships, or you can even have very strict one-to-one. So it's quite rich in capabilities. So what it would look like in this use case would be something like this. So we would have, as a data modeling for DynamoDB, is that we would have sort keys, or we would have partition keys. So meaning that the rider ID, which could be the rider or the driver of that vehicle. So if I'm the rider, my rider ID would be my partition key, seeing in DynamoDB as the main key value. And then I would have my trip information, when it started, who is my driver, what are my attributes, and that could be flexible based on the ride that I'm taking. And the same goes for the driver itself, having the trip info, who will be my rider, who will be part of my trip, etc. So in this user case context, this is a really good, nice example of they would most likely benefit immensely by having a DynamoDB for the real-time processing side. And if they need to scale globally, DynamoDB allows that, but so does Aurora. So if they would like to stick with the global approach, but still have a relational database, another option could be having an Amazon Aurora global database. So it's not always just one option fits that purpose. It might be multiple options, but you need to be able to choose the best one. So let's take example of something that is existing, that is very similar of the use case I'm talking about. Let's talk about Lyft. So they use a lot of DynamoDB. So they do massive scale and they do bursts of like peak performance, and they do it quite gracefully. So they are in 200 cities. They do like 40 million rides per month, 8 times traffic during peak hours. So it's quite fluctuating when it comes to the load, what's happening. And they have mission critical transactional data, like GPS location data. And they are able to handle the rapid growth cycles with a small team when they're using DynamoDB. So that is a very typical use case. And yeah, so I think what I will do here, because I know there's a lot of data and there's a lot of topics to handle, I will stop sharing and let me open up for questions. So the thing that I want to summarize with you is that the thing you need to take with you, and next week we are going to experiment with this, and we are going to walk through different relational databases and also non-relational ones, is that you will not be able to know all of the products when you go into your exam, and that's not the need. Not even if you're doing your data engineer or like in the past, those that did the database specialty, you don't need to know all the services, but you do need to know which category they fall under and which use case they would serve a purpose for. So that is like the main thing to understand. There are certain things like very typical questions that I will help you with in the exam prep phase. But for now, understanding the RDS, Amazon Aurora, and DynamoDB is enough to pass your exam. But I've been speaking a lot, so let me see if there are questions that I haven't answered yet. And also feel free to unmute yourself and ask any questions that you might still have. I'm trying to find my chat. All right. I don't think there's anything I haven't answered yet. So what I will do, I will there's actually one. What is the share volume-wise for Amazon RDS for Postgres? So when you look at the use cases, like anything you have in relational databases side, so when you have the choice of, let's say you have Amazon Aurora for PostgreSQL, or let's say MySQL type of engines, the typical reasoning why you choose something over the other is most likely some of the like smaller functionalities in there. So let's say that you're moving a database that is using a lot of code that is developed specifically for MySQL. The lift and shift is typically easier when you choose MySQL over, let's say, Postgres. So it's fundamentally certain differences with the use cases. Is it already existing? Is it not existing? One of the easiest way of doing relational database design is, of course, if you have the opportunity to start from scratch, and then you have all those options that you have with databases up for be chosen. And even then, if you choose from multiple options, you might choose something over the other, even if it's much more expensive, to have a certain feature in the database. So some of the like commercial grade databases have a lot of features that the others may not have. So you might be choosing it based on a feature. Let's take an example. Some of the bigger and smaller databases have a very big variety of spatial data, so like GPS data capability. You might choose then the database that it fits your purpose the best if you're having a lot of map data that you have to have and coordinates data in your database. So it's typically also in that use case, it's purpose built. So that is something I would mention. But yeah, I will share all the slides. So Sanna will be able to share you the slides. You will also get the example that I showed you. And next week will be the immersion day. And then remember that when you look at the calendar, there will be the exam prep. I highly recommend for you to take the exam prep before going to the exam. So that will also cover the section of databases and what are the typical questions. So, hey, thank you, everybody. Thank you for your time, and hopefully see you next week.